This reciprocating compressor has been boosting natural gas up to sales pressure for 70 years. That's a remarkable lifespan for a piece of equipment like this. And then maybe it isn't, when you consider the kind of maintenance and care it's received. Now, a good operator can do a lot to prolong the life and maintain the efficiency of units like this. Learning how to do that is what this module is all about. This is the first section of a 5-section module on reciprocating compressor operation. In this section, we'll take a look at a typical compressor package, including its components and subsystems. Now, before going any further, it's important to note that you should have completed the modules Reciprocating Compressor Principles and Basic Principles of Pressure and Temperature, or have had operations experience equal to the material contained in those modules. Now, if you haven't, we strongly recommend you complete those modules before studying this one. To operate a compressor efficiently, an operator must know the components and subsystems of the compressor package. So let's review those things now, using a compressor package to show you the examples of certain components. We'll start with the cylinder and piston. Here's where most of the action occurs in a reciprocating compressor. In the cylinder, a trapped volume of gas is compressed by the piston, increasing the gas pressure. The gas is then discharged, and a new volume of gas is again compressed by the piston. This cycle repeats itself hundreds of times per minute. When gas is compressed, it generates heat. So to help control heat buildup and prolong cylinder life, cylinders have passages for cooling water. Keeping things cool is vitally important in operating a reciprocating compressor, because excessive heat buildup can damage equipment, resulting in lost revenue and costly repairs. So, in addition to cooling passages, most compressors have lubricant added in the cylinder walls to reduce wear from the friction generated by the back and forth motion of the piston. Now, other compressors use special material, for example, Teflon, to reduce friction. To further reduce wear on the pistons and cylinders, rings are mounted in machine grooves on the piston. The primary function of these rings is to create a pressure seal that prevents gas from leaking from one side of the piston to the other. Each cylinder also contains 2 sets of valves, suction and discharge. These valves look similar, but gas travels through them in only one direction. As suggested by their names, a suction valve allows gas to enter the cylinder for compression, while the discharge valve lets the compressed gas leave the cylinder. Although there are several different types of valves, they all work on the same principle: differential pressure. Like water seeking its own level, gas will travel automatically from a high pressure to a low pressure area. So in the case of a suction valve, a lower pressure inside the cylinder and a higher pressure outside the cylinder cause the valve to open, allowing gas into the cylinder. The reverse is true for a discharge valve. The compressed higher pressure gas escapes the cylinder to a lower pressure area through the discharge valve. Moving along now to the crank end of the cylinder, we find packing that surrounds the piston rod. Constructed of rings and cups in a cage, packing is used to prevent pressurized gas from escaping to the atmosphere, or crankcase. To reduce wear, the packing may have lubrication ports, or be constructed of special materials, such as Teflon. Like the cylinder, The packing can also have cooling vents for water circulation. Within the compressor, there are two types of rods: piston and connecting. A piston rod joins the piston to the crosshead. The crosshead converts the rotary motion of the crankshaft into the back and forth motion of the piston. The crosshead must be held in very close tolerance to the crosshead guides to ensure horizontal, level motion of the piston. Slippers, shoes, and shims are used to keep this close tolerance. Here again, lubrication is important, and crosshead slippers are lubricated from the crankcase or through ports. The connecting rod joins the crosshead to the crankshaft, transferring the circular motion of the crankshaft to the horizontal movement of the crosshead. The frame of the compressor houses the crankshaft and provides central support for the crosshead guides and the cylinders. Now let's talk about bearings. Compressors have main bearings and rod bearings. Main bearings support the crankshaft at the center line of the frame. Rod bearings, located at each end of the connecting rod, allow the rod to rotate smoothly with the motion of the crankshaft. Both main and rod bearings are types of sleeve bearings. Once again, lubrication is vital. In fact, lubrication must be continuous to keep friction minimized. Between the crosshead bed section and the cylinder is the distance piece. This is where you'll find the wiper rings and pressure packing. The distance piece prevents any processed gas from leaking into the crankcase and provides a way to vent any leaking gas away from the compressor. In order to prevent lubricant in the crankcase from entering the cylinder, wiper rings are placed between the distance piece and the crosshead bed section. The collected lubricant is drained from the distance piece to a sump line, while the pressure packing on the crank end of the cylinder seals gas in the cylinder. Before gas enters the compressor, it goes through a scrubber like this one. Liquids and contaminants are separated from the gas stream inside the scrubber. They drop to the bottom of the scrubber and must be emptied. Now, if the liquids and contaminants are not periodically dumped, they could pass into the equipment, causing compressor damage. These are called pulsation bottles. They are used to reduce pulsation in gas pressure caused by the reciprocating movement of the piston. The bottles, mounted on the suction and discharge sides of the cylinder, help reduce gas pressure fluctuations through the compressor, lowering the damage and wear caused by excessive vibration. As we mentioned earlier, gas temperature increases as gas is compressed. So to control gas temperature, discharged gas is passed through a cooler to remove some of the heat. Usually it's an aerial cooler with separate passages for compressed gas, water, and lubrication. Now, part of the cooler may have passages for water to cool the prime mover and compressor cylinders. In addition to the suction and discharge valves, there are a lot of other types of valves in the inlet and outlet piping of a compressor. Check valves ensure that gas flows in one direction only. Relief valves prevent overpressuring of the compressor and piping. Vent valves allow depressuring of a single compressor cylinder or the complete compressor package. And recycle valves allow the same gas to flow through the unit a second time. The last of the main components for a reciprocating compressor is the control panel. It is a central location for switches, gauges, and indicators. If there is no central control panel, the compressor and prime mover must be controlled and monitored remotely or with separate controls around the package. Those are the main components of the reciprocating compressor itself. Now let's take a look at the prime mover. In today's oil and gas operations, there are two kinds of prime movers used with reciprocating compressors: internal combustion engines and electric motors. Electric motors, coupled to the compressor crankshaft, are being used more often these days to eliminate hazardous air emissions and to cut down on maintenance and fuel costs. Internal combustion engines, however, are still the most common prime movers for reciprocating compressors. They are either a 2-cycle or 4-cycle engine. Engines for compressor packages are considered either integrated or separable. Integrated engines are a part of the compressor frame and cannot be separated from the compressor package. They operate in the 250 to 350 RPM range. Separable engines are connected to the compressor with a coupling and can be attached to any load. They usually run between 600 and 1,000 RPMs. The ignition system on a prime mover performs a couple of different functions. First, it provides electric current for ignition. It also gives spark for combustion in prime mover cylinders. Finally, it is an integral part of the safety shutdown of the compressor. When the control system senses an unsafe condition on the compressor package, the ignition system will automatically trigger a shutdown. There are two types of ignition systems, magneto and electronic. Magneto systems are typically found on older compressor packages, while the newer ones have electronic systems. And that brings us to the end of Section 1. So far we've covered the components and prime movers for compressor packages. All right, take some time now to read and study this material in Section 1 of your manual. Fill in the blanks and ask questions if you do not understand something. When you've finished, we will continue the module with a look at compressor types and designs. Now that you are thoroughly familiar with the components and prime mover of a compressor package, let's move into compressor design and type. This is the second section of a 5-section module on reciprocating compressor operation. In addition to compressor design and type, this section will also cover gas flow and auxiliary systems. Compressors come in different types to accommodate different compression requirements. Now let's take a look at the most common compressor types. In an integral unit, the prime mover and the compressor are combined, sharing the same frame and crankshaft. The power cylinders are usually vertical and the compression cylinders horizontal. In another design, a V configuration is used with the power cylinders on both banks and the compression cylinders on the horizontal. In separable units, the prime mover is coupled to the compressor crankshaft. This is always done when the prime mover is an electric motor. In a horizontal balance opposed setup, there are horizontal cylinders on each side of the crankshaft. Usually the opposed cylinders are compression cylinders, but in some cases they are a combination of power and compression cylinders. The balancing of weight and forces on each side makes the compressor operate smoothly. Because horizontal balance opposed describes only the compressor cylinder setup, the compressor package itself can be integral or separable. Regardless of whether the compressor is integral or separable, the path of gas through the unit depends on the type of cylinder and whether it is a single or multi-stage compressor. A single-stage unit compresses gas from suction pressure to discharge pressure in one step, with one or more cylinders in parallel. After the gas is compressed, it is released into the discharge line, where it may go through a cooler before flowing to its final destination. Single-stage compressors can only increase gas pressure by a certain fixed amount. Factors that dictate how much a single-stage compressor can increase gas pressure include increased gas temperature, rod load, and horsepower requirements. So in order to obtain higher discharge pressures, there must be a multi-stage compressor package. In a multi-stage unit, gas is compressed from suction pressure to discharge pressure in stages. The discharged gas from the first stage of compression flows to a cooler. Before entering the second stage of compression, the gas goes through a scrubber. In the second stage, the gas pressure is further increased. This process continues until there is enough pressure for sales requirements or field applications. A reciprocating compressor, like any equipment, is designed to be operated within specified ranges. Three critical areas are discharge temperature, rod load, and maximum working pressure. Manufacturers determine the proper discharge temperature of a compressor. Gas discharge temperature is affected by many things, including inlet gas temperature and pressure, the weight of the gas, compression ratio, and valve operation. The gas discharge temperature is normally not above 300 degrees Fahrenheit. Rod load refers to the structural limit of the compressor package. This is the maximum continuous operating force the compressor can safely withstand. Rod load is a force exerted on the piston rod, and bearings during the compression cycle. Pistons have two rod load factors, compression load and tension load. Compression load is the load on the piston rod as it moves toward the head of the cylinder. Tension load is the load on the piston rod as it moves toward the crank end of the cylinder. Rod load, also known as frame load, is figured by the manufacturer to ensure that the compressor does not exceed its capacity. Excessive rod load can be the result of valve failures, as well as increased or decreased cylinder pressures. Excessive rod load will cause mechanical failure, such as bent or broken connecting rods or bearing failure. To put it bluntly, excessive rod load will shut you down. Now, our final design point has to do with maximum working pressure, which is the highest discharge pressure the compressor can handle while operating continuously. The maximum working pressure provided by the manufacturer should never be exceeded, or damage to the equipment can result. All right, let's spend some time now talking about cooling systems. The purpose of the cooling system is to prevent overheating. Overheating can cause compressor damage, and that means costly repairs. In most cases, there is a single cooler used for several cooling purposes. The cooler may have multiple passages for lube oil, jacket water, and the compressed gas stream. That means the compressor and internal combustion engine can be kept from overheating by the same cooler. Smaller compressors may use air cooling to remove heat created during compression. Fins surrounding the cylinders increase the surface area and provide adequate cooling. However, this does not give sufficient cooling for most large compressors. Instead, on larger compressors, a water circulation system is used to provide compressor cooling. Pumps move water through the cylinder jackets and through the cooler. After being cooled, the water is then recirculated. Discharge gas is also piped to the cooler and cooled in an air-gas exchanger. From there, it can flow through a scrubber to the suction valve for the next stage of compression, or away from the compressor for further processing, or to a pipeline. In the prime mover, coolant is pumped through the engine, the cooler, and a lubricant cooler. Earlier, we talked about how important lubrication is to various parts of compressor operation. Lubrication systems prevent or reduce the wear of components due to friction, and these systems remove heat from the moving parts, providing longer life and less chance of damage to equipment. To stay effective, the lubricants should not be allowed to deteriorate or become contaminated. Lubricant levels, temperatures, and pressures should all be maintained within manufacturer's specifications. Generally speaking, compressor packages have two types of lubrication systems. In one system, lubricant is pumped to the bearings and then returned to the sump. In the other, very small amounts of lubricant are force-fed to high-wear areas, like the compressor cylinders, compressor packing, and prime mover cylinders. In the force-fed system, most and sometimes all the lubricant is used up during operation. It is extremely important that the person responsible for operation consistently check the oil level on the compressor, either by looking at the sight glass or the dipstick if one exists. Then be sure to add oil as needed. On the prime mover, the lubricant continually circulates through the lubrication system and will eventually deteriorate. So the lube oil must be checked and analyzed at regular intervals and changed when needed. This is similar in nature to changing the oil in your car at regular intervals. To help ensure safe operation, safety and control systems are built into the compressor package. The package is designed to shut down when a condition that is unsafe or that could damage equipment occurs. There are two kinds of control systems, electric and pneumatic. On electric control systems, these unsafe conditions signal the ignition system to ground and to shut off the fuel supply to the prime mover. With a pneumatic control system, the fuel supply to the prime mover is also shut off, stopping the compressor package. Other safety features include rupture discs and safety relief valves, which are installed in the compressor lines to relieve excess pressure. If, for example, a discharge valve were to malfunction, causing a sudden increase in pressure, the safety relief valve would open to release the gas into a vent, or flare line. A rupture disc in the same situation would simply burst to reduce pressure. Each compressor package has a control system to limit the speed and output of the unit. This system is designed to maintain a safe operating speed, ensuring a proper flow of gas through the compressor. There are several methods of controlling speed and output within the system. Your student manual contains a detailed description of these methods in Section 2. Please be sure to study them in detail and ask questions if you do not understand these methods. Well, that brings us to the end of Section 2. It's time now to stop the tape and read this section in your student manual, filling in the blanks and answering the questions at the end of the section. I'll see you when you're finished. Running a compressor package efficiently is similar in certain ways to being an airline pilot. Part of flying a plane is to establish normal operation for the aircraft, and then continually monitor all indicators to determine when a system may be exceeding its limits or is malfunctioning. The same is true for operating a reciprocating compressor. This is the third section of a 5-section module on reciprocating compressor operation. In this section, we will cover the indicators for normal operation of the compressor package. In addition, you will see how to do scheduled operational checks and recommended inspections to minimize disruptions in compressor operation. All compressors are equipped with key operational indicators. Sometimes these indicators are located on a control panel. At other times, they are on the unit itself. Let's take some time now to go over them. The cylinder jacket water temperature gauge indicates the temperature of the water in the cylinder jackets. The crankcase temperature gauge registers the temperature of the oil in the crankcase. Normally, this is between 125 degrees Fahrenheit and 150 degrees Fahrenheit. The gas discharge pressure gauge shows you the pressure of the discharge gas, while the gas discharge temperature gauge indicates its temperature. The gas suction pressure gauge registers the pressure of gas entering the cylinder, while the gas suction temperature gauge shows its temperature. The compressor RPM gauge indicates the crankshaft speed in revolutions per minute, or the relative speed of the piston's movement within the cylinder. The speed should remain constant, as set by the speed control settings for the compressor package. The oil pressure gauge shows the pressure of the oil supplied to the bearings. Normally, this is within 20 to 40 psi. The lubricator pressure gauge gives you the pressure of the lubricant supply to the cylinders and packing. The gas interstage pressure and temperature gauges register the pressure and temperature of the gas as it passes between compression stages. All of the functions we've just listed should remain within an established normal range, or within the range of the compressor's operating specifications. Vibration sensors are located on the compressor and sometimes on the prime mover. If excessive vibration occurs, these sensors send a signal to shut down the compressor. Operators should immediately report any unusual or excessive compressor vibration, because this often signals a major mechanical problem. The prime mover also has key operational indicators. Some are located on control panels, while others may be on the mover itself. Now, these indicators are different for electrical and internal combustion engines. Your student manual contains a detailed list of the various indicators. Please, study it in great detail, especially for the type of prime mover in your unit. There are additional indicators that can tell the operator problems are about to occur. For example, there is a sight gauge on the scrubber that indicates liquid level. High liquid levels in the scrubber will cause a compressor shutdown. Sometimes there is a low level sensor that causes an alarm to sound or will shut down the compressor. Leaks are another indicator of a possible malfunction. The compressor or prime mover may have oil, gas, or water leaks. Gas leaks are potential safety hazards and should be scheduled for immediate repair or action taken to minimize the leak until maintenance can be done. All leaks should be thoroughly investigated to see if they indicate an operational problem or malfunction. Finally, mountings maintain the stability of the compressor package. Loose mountings may be the result of excessive vibrations, wear, or a loose fit. In separable units, loose mountings can cause misalignment and complete compressor failure. Well, that about wraps it up as far as indicators go. Now, as an operator, it is vitally important that you pay close attention to the gauges and sight glasses that monitor your compressor package. Finding an operational problem early will go a long way toward maintaining a safe and efficient unit. And so will daily inspections. A compressor package requires at least a daily inspection to ensure continued smooth operation. It's a good idea to have a checklist to make sure all the inspection points are covered. The appendix of your student manual contains an example of such a checklist. A daily log is also useful to establish a record of normal operations. This log can be completed as the inspection is being performed. Your student manual also contains an example of a daily log sheet. Let's briefly walk through a daily inspection to give you an idea of what to look for. Starting with the scrubber, check and record liquid levels and supply pressure. Then look over the fittings and seals. Tighten them if necessary. Adjust the pressure regulator as needed. Manually trip the liquid level controller while observing the function indicator and dump valve response. The valve should respond smoothly, and there should be a decreasing level in the sight glass. If the automatic dump valve is not working, manually dump the liquid and report the unit for repair. On the lubrication system, look for oil leaks around the compressor package. First, minimize all oil leaks, and then repair them as soon as possible. Be sure to record areas where oil leakage exists. Check the lubricant levels and pressures and record that information. Then check the engine crankcase oil level. Inspect the color of the oil to see if it is contaminated. For example, white or creamy colored oil would indicate water in the oil. Also inspect the pumps and injectors for normal operation. On the electrical system, look for damaged wires on the ignition unit, coils, and spark plugs. Be sure all connections are tight and report equipment which needs replacement. Moving on. Check for coolant leaks around the compressor package. Listen for any unusual sound or vibration in the cooler. Taking safety precautions, note the condition of the belts. After checking the level, add coolant as needed. Now check for gas leaks around the compressor, especially at valves, regulators, and the distance piece. If leaks are observed, schedule repair as quickly as possible because of the fire or explosion hazard. Be sure to inspect the mounting fittings for wear, tightness, and vibration. On the pulsation bottles, check for leaks and listen for strange noises. Also check for excessive vibration. On the compressor itself, check and record all the key indicators we discussed earlier. And do the same thing with the prime mover. In addition to daily inspections, periodic inspections should be performed as warranted by past performance, or at least once each year. Periodic inspections should be done only by qualified personnel. So while the operator may not be responsible for actually doing the periodic inspection, they should still know the inspection requirements for the specific compressor package. Before any inspections of moving components are undertaken, the compressor package must be isolated from all power sources as outlined in your company's lockout-tagout procedures. Your student manual itemizes those elements that require attention during a periodic inspection. You should carefully study those things when you read this section. And that brings us to the end of Section 3. It's now time to stop the videotape and read over this section in your student manual, filling in the blanks and answering the questions at the end of the section. When you've finished, we'll come back with a look at startup and shutdown procedures. Now that you have a fundamental overview of the compressor package and the inspection procedures, it's time to move into operations. This is the fourth section of a 5-section module on reciprocating compressor operation. In this section, we will show you startup and shutdown procedures for a typical compressor package. Starting a compressor package involves loading the compressor and starting the prime mover. A startup can be done by one operator, though in some locations the task may be safer and more efficient with two. Startup begins by determining the cause of compressor shutdown. Logically, the first place to check is the indicators to see if some malfunction has occurred. If so, the condition must be corrected before continuing. If, however, the shutdown was due to routine maintenance or an otherwise normal shutdown, you may continue with the startup procedure. The compressor loading sequence is determined by the presence or absence of a check valve. The check valve prevents discharged gas from backing up into the cylinder. If there are interstage suction and discharge valves, each discharge line should be examined for a check valve. On compressors without interstage valves, look at the main discharge line for a check valve. The actual startup procedures depend on the type of prime mover and whether each stage has separate suction and discharge valves. Now, for our demonstration, we'll be starting up and shutting down a compressor package which has a 4-cycle internal combustion engine, multi-stage compression, a single suction line valve, a single discharge line valve, and a check valve in the discharge line. Now, your local compressor package may be different, so be sure to go over procedures for your facility before taking any action. First, as we mentioned earlier, determine the cause of the compressor shutdown. In this case, we will say it was a normal shutdown. If it was not, it would be your responsibility to determine the problem and get it repaired. Next, be sure the suction valve is closed. Then check to be sure the vent valves are open. Now confirm that the bypass valve is open. Slowly open the main discharge valve. This will seat the check valve. Do a complete walk around of the unit to be sure the area is clear of all personnel. Now activate all shutdowns on the control panel and open the air starting valve. Then partially open the manual fuel valve. This will start the engine as the fuel is ignited by the spark plugs. If the engine does not catch within 5 seconds, repeat the cycle. When the engine does fire, close the air starting valve. Now idle the engine to check the coolant and lubricant circulation. The compressor is now ready for gas loading. First, close the vent valves. Then confirm that the bypass and discharge valves are still open. Now, open the suction valve. Doing this allows the same gas to be continuously cycled through all the stages without compressing it up to sales pressure. Once you close the bypass valve, which is the next step, the gas will be compressed up to discharge pressure and leave the system through the discharge line. Now adjust RPMs to the desired level and place the engine back in automatic speed control. Verify that all interstage and discharge pressures are normal. Then take a final walk around the unit to ensure that there are no gas leaks, unusual noises, or abnormal vibration. Now, in order to shut down this type of package, this is the recommended sequence. First, put the engine in manual operation. Then reduce the engine RPMs. Slowly open the bypass valve. Next, close the suction valve. Check to be sure coolant and lube oil are circulating. Also make sure there is engine jacket water circulation, and note unusual noises or vibration. Now push the stop switch on the control panel. Your next step is to vent the suction line. Now close the discharge valve and vent the discharge line. Finally, tag all other valves that have been moved from their normal operating position. Well, that brings us to the end of Section 4. Please, stop the videotape and carefully read this section in your student manual, filling in the blanks and answering the questions at the end of the section. Now, when you have finished reading and discussing Section 4, I'll be back to talk about troubleshooting. See you shortly. While inspections can go a long way toward preventing problems with reciprocating compressors, there will still be times when things go wrong with the package, and that's where troubleshooting comes in. This is the final section of a 5-section module on reciprocating compressor operation. Now in this section, we will discuss troubleshooting. All reciprocating compressors require troubleshooting at one time or another. Control panels may be helpful in identifying the source of a problem, but many symptoms can also be detected by sound and visual clues. Since problems can arise in either the compressor or prime mover, being visually aware of operating changes and alert to noises out of the normal range can be one of your best ways to find those problems. Appendix A of your student manual contains an extensive troubleshooting guide, including the possible causes of a problem and the proper corrective action that should be taken. These are just a few of the potential problems that can occur with the reciprocating compressor package. Each of these affects the operation of the package to a different degree, so it is vitally important that you carefully study this material in your student manual so you'll know what to do should these problems occur. Be aware that malfunctions can occur not just on the compressor itself, but also on the prime mover, or on the compressor and prime mover. Knowing what to do when you encounter any of these conditions is important for a number of reasons. Your safety and the safety of your fellow workers could depend on your ability to properly diagnose a compressor package problem. In addition, the better you operate that piece of equipment, the more profitable it is for the company. And that's eventually good for all of us. And that brings us to the end of this module. Please read over Section 5, filling in the blanks and answering the question at the end of the section. Operating a reciprocating compressor package is a complex job. If there is anything we have covered in this module that you don't quite understand, now is the time to ask questions of your instructor. Remember, the more efficiently you do your job, the safer and more productive it is for everyone around you.